G6, the work-energy theorem. We already did this, in a sense, in the other section. So here's just a quick little summary of what we did in the other section, where we had the force times the distance, and since it's a constant force, constant acceleration, we used two kinematic formulas from an earlier chapter and obtained the result that the work done is equal to the change in the kinetic energy. And that is the work-energy theorem. The work-energy theorem says the work, and here to emphasize, we could say of the net force, or of the resultant is a word used for like adding up all the forces as vectors, of the resultant force is equal to the change in kinetic energy. The work-energy theorem. Now let's apply this. This has tremendous power and use, and let's see what it can do. And the first application that we're going to do, the first case, is with gravity, and it's one where we already know the answer. I'm going to show this new method using the work-energy theorem to find the velocity of a ball if you drop it from rest and it's just about to hit the ground. 2AD, v squared minus v naught squared, that's one of our kinematic equations. And we're going to call, say, going down here, positive, like this. So then that's 2g times d is v squared. We're going to start from rest because we're going to drop it. And that means that the velocity is equal to the square root of 2g. Let's use h. A lot of times folks like to use h for a height. In other words, here we're dropping the ball from height h, down is positive, and right before it hits the ground, we're going to have this velocity. That's it. Now, how do you do this problem using the work-energy theorem? Well, the work-energy theorem says, well, if we write the work down, which is force times d in general, this is equal to the 1/2 mv squared minus 1/2 mv naught squared. So here we're dropping from rest. All right, so we don't have any velocity at the beginning. And here we have forces mg, d is h, and this is going to be equal to 1/2 mv squared. The m's cancel, and the v squared is 2gh, and that gives us the same answer as before, and somewhat easier because if you remember 1/2 mv squared and mgh, you're finished. Here, this formula, 2AD is v squared minus v naught squared. A little bit more effort to remember that one. So using the work-energy theorem, which you can think of as a conservation of energy principle, gets the problem done very fast. Next example is the spring. Now, if you have a spring, there's a very, very nice law that's simple and is pretty good as approximation. It's called Hooke's law. So what we're going to do here is consider here a point of equilibrium where there's no stretch. And then here, we're going to stretch some mass m. That the force of the spring is going to be opposite. It's going to pull you back, minus kx, where this k is called the spring constant. In textbooks, they usually will use, for this one, a lower case, and the capital K is for kinetic energy. Kinetic energy, that's your 1/2 mv squared. And your little k here is the spring constant. So here, we're going to pull the mass, do some work in pulling the mass out, and there's going to be no friction. And then we're going to let go. It's kind of similar to the problem we just did here. We picked up the mass, the stone or the block, and when we did that, the work that we did was actually mgh. But then when we drop it, gravity does the mgh back again to translate it into the kinetic energy. So let's go ahead and do that. But how do you do that when x is not, the force is not constant? Well, here's what we do. We go back to this problem and we notice that if we do a plot here where we're looking at, say, a constant force, mg, say this is at height, this is at level force is mg, and say here is the height that we moved, that mgh is the area under the graph. So that is the work. So whenever you have, say, force here, versus, say, distance, like this, like a plot, force versus x, that the area under the graph gives you the work. So if we use that principle here, or if we have x, we have f, when you have kx, the force I have to apply is going to be plus kx to counteract the negative kx. I'm going to plus pull it, so I would have this equation here, and we'll go ahead and let this be x. This is the x-axis, and this is the force axis, and this is the equation F is kx. Now I'm doing a plus sign here because I'm taking it from the equilibrium, pulling it to the right. I have to pull it more and more force to get it out there. So this is the correct equation for the setup, and I need the area under the graph. Now the area is the area of a triangle. It's 1/2 the base, which is x, times the height, which is kx, going up this way. So that's 1/2 kx squared. So now if I want to do the work-energy theorem, I'm going to let this thing go and have the spring now do the work coming back. I'm going to have 1/2 kx squared equals 1/2 mv squared minus 1/2 mv naught squared. And since I'm letting this go for rest, that's 0. And here I'll have kx squared is mv squared. And that means here v squared is k over m x squared. So v is the square root of k over m times x. That's very powerful, and that's a force that's varying. The acceleration is not constant. Now with calculus, here's how we would do this area. We would go from 0 to x, f of x dx, 0 to x, kx dx, and that's the constant can be pulled out. This is x dx, and that would be integration is x squared over 2, and you go from 0 to x, and that would be kx squared over 2 minus, you put in 0 for the x for the second one, which is going to get you 0. So the work done is 1/2 kx squared. I would like to show you that when the spring is pulling the mass back, it does the same amount of work. So here, we're going to go from x to 0, and the force is going to be minus kx because it's pulling to the left now. and we're moving from x to 0, dx. This is going to be minus, from x to 0, kx dx, which will be equal to minus k. When we integrate this, we'll have x squared over 2 from x to 0, and that's going to be k 0 squared over 2 minus x squared over 2. The minus signs are going to cancel, and you're going to get 1/2 kx squared. Okay, now I want to show you that, if this thing bothers you, it did bother me to use x and x. What we do to fix that, we just go to some capital A instead. All right, and if we do that, we go from 0 to A. Here's kx, dx. We're going to do this one over again here. And this is kx from 0 to A, dx. K x squared over 2, 0 to A now. And that's k, where you put in x is A, and then subtract when you put in 0 for A, and you get 1/2 ka squared. Okay? And if you want, you could just say A is x. It doesn't matter. But anyway, it used to bother me to have the x here and there, so I just wanted to point out you could always do it this way. Then you set up your problem where you take the spring and you pull it out from equilibrium out to some A. In fact, we actually will do this later. Call this the amplitude. When this thing lets go and we have some kind of oscillations going on, we'll be doing oscillations and the harmonic oscillator later in the course. Very powerful stuff too.